History of Vector Analysis, Episode 17, Modern Vectors, Part 1. You are here. Hey, it's old Doc Oler. Welcome. Today's episode is the climax of the entire series. It's actually a two-part episode. I tried to distill it down to one, but there's just too much I feel I need to say. So it is my intention, for what that's worth, that you will set aside the time to watch this episode and the next one back to back. Okay, in the previous episode, I discussed how James Clerk Maxwell helped quaternions go mainstream in the physics community by incorporating them into his 1873 treatise on electricity and magnetism. He wrote quaternions side by side with the, at the time, standard Cartesian component math. His motivation was his attraction to the visual attributes of the vectorial concept, field points represented by a single geometric magnitude and direction rather than as separate x, y, and z components or as a mere algebraic string of numbers. He argued that this ability to visualize the field, via quaternions in this case, was inherently valuable. He acknowledged William Thomson's point that in practice, the quaternion approach to evaluating specific problems didn't usually save much labor. He also acknowledged that he took issue with the way some of the quaternion methods ended up being used. Meanwhile, in the outside world, the Industrial Revolution was raging, including the revolution in electricity and magnetism. Alexander Graham Bell had patented the telephone in 1876, and Thomas Edison patented the first practical incandescent light bulb in the year 1879, which was the year that Maxwell died. All of these electrical systems, both the power-oriented ones and the communications-oriented ones, experienced numerous technical problems. In order to understand the causes of these problems and to eliminate or compensate for them, a comprehensive mathematical theory for E&M was needed. And the best theory out there was Maxwell's. Unfortunately, Maxwell's treatise was long, filled with digressions, and aimed at scientists rather than working engineers. Both the Cartesian math and the quaternion math were difficult for the engineering community to use effectively. Okay. In the 1880s, two very different men independently developed modifications to Maxwell's quaternion approach. While not identical, these two sets of modifications were close enough that they were later merged. This double episode is the story of these two guys and the modern vector analysis that they produced. The first of these two men was Josiah Willard Gibbs, a Yale professor working at a prestigious university in what was at the time a scientific backwater, the United States. Okay, practical inventors the U.S. had in spades, but theoretical types, not so much. Gibbs was one of the few. Gibbs read Maxwell's treatise on E&M when it was published in 1873. As an academic, he was no doubt familiar with the Cartesian component math in Maxwell's papers, but the quaternion approach was apparently new to him. He proceeded to acquire a copy of Tait's treatise on quaternions, which we discussed in an earlier episode. Like Maxwell, he was struck by both the pros and the cons of quaternions. After Maxwell's death in 1879, Gibbs took up what he saw as Maxwell's challenge to improve the quaternion methodology while keeping their vectorial spirit. The result was a relatively short pamphlet entitled Elements of Vector Analysis, which appeared in 1881 and which was expanded in 1884. Importantly for our story, Gibbs did not formally publish this document. You can see right here, not published. He had it printed privately and then mailed copies of it to about 130 scientists and mathematicians worldwide. I'll come back to this in a moment. One of the people Gibbs did not mail his pamphlet to was a Brit named Oliver Heaviside. Heaviside lived in London, but he was no academic. He was a commoner with no university education at all, just a working stiff, but with an inherent talent for mathematics. He came to work as a telegraph operator in England and became interested in the theory behind it. He also obtained a copy of Maxwell's treatise on E&M when it appeared in 1873, and then, like Gibbs, turned to Tait's book on quaternions. Later, in the 1880s, he started publishing original papers on E&M, mostly in a journal called The Electrician. This was not a prestigious journal. It was more like Popular Electronics, but his work was often brilliant. He organized these papers with some additional material into a book entitled Electromagnetic Theory, published in 1893. Also like Gibbs, Heaviside took up Maxwell's challenge of improving quaternions into something more practical and published his first vector paper in 1883. He was unaware of Gibbs' unpublished work that had appeared 2 years earlier, not being on Gibbs' personal mailing list. Okay, according to Crow, Heaviside first saw a copy of Gibbs' Elements in 1888, after his own work on vectors was essentially complete. Okay, there were differences, but in key ways, the two approaches, Gibbs and Heaviside's, were remarkably similar. What did Gibbs and Heaviside do? Let me reiterate some stuff from earlier episodes for the purposes of compare and contrast. Way back in the 1840s, Hamilton discussed the properties of a subset of quaternions in which the real part was set to 0. If you multiplied two such objects, the non-zero terms were these. Using Hamilton's rules for multiplying the imaginary ijk's, shown in the box, the result could be expressed like this: a scalar part and a vector part, or what we would today call a dot product and a cross product. It was Hamilton who defined the del operator, but it was Tate who went on to develop it to the point where it could be applied to Hamilton's zero real quaternions. He showed that the result also had a scalar part and a vector part. The scalar part is close to today's vector dot product, except that it has this extra minus sign. The vector part would be identical to today's curl, except for the fact that ijk are imaginary. Note that the minus signs in the vector part are all due to the anticyclic multiplications. ji is equal to negative ij. This chart is the start of the big reveal. Both Gibbs and Heaviside independently defined a new quantity v, which they both called a vector. Like the Hamilton-Tate vector, it was a 3D object, not a 4D object. Also, like the old vector, the new one was a single mathematical object that had a magnitude and a direction. It is also expressible in terms of three components, each of which was proportional to a unit vector ijk pointing along a different axis. However, the new vectors differ from the old vector in that here the ijk unit vectors are real rather than imaginary. Okay, notice that I'm expressing the new ijk's with a black typeface rather than colored ones to indicate this. Gibbs and Heaviside then proceeded to use these 3D non-imaginary vectors to define new operations as replacements for the quaternion, scalar, and vector products. Okay, I'll begin with the scalar products. This is compare and contrast stuff, okay? Using Hamilton's multiplication rules for ijk, which is what he based everything else on, he showed that the product of two zero real quaternions was this: a total of 3 real terms and 6 imaginary terms for a total of 9 terms. He then defined the scalar part of this expression as the sum of the 3 real terms, all of which are negative. Okay? Gibbs and Heaviside have just defined new vectors in which the ijk are real. What do you get when you multiply two of these vectors? Well, you do still get 9 terms, but this time they are all real. So what is the analog of Hamilton's scalar product? I'm not going to defend what follows any more than they did. I'm simply going to state it. Gibbs and Hamilton simply defined the scalar part of these two vectors as the same as Hamilton's definition, with the exception that the minus sign is replaced with a plus sign. Just 3 terms, not 9, so no cross terms. Today we recognize this as the vector dot product. Okay, both Gibbs and Hamilton completely understood that it was not sufficient to simply define the scalar product. They knew that they also had to define the ijk multiplication rules required to produce it. To reduce the 9 terms of a true multiplication of v1 and v2 to these 3, working backwards, these are the ijk rules that you must have. Okay, so Gibbs and Heaviside state that these are the dot product rules for ijk to do scalar multiplication. Poof. Now let us consider Tate's convergence, the scalar portion of the del operator acting on a quaternion. What is the analog of this using these new all-real vectors? Gibbs and Heaviside both do the same thing. They define the result of the operation as identical to the Hamilton-Tate result, except for changing that negative sign to a positive sign again. The major effect of this, as far as G and H are concerned, was that the change in sign meant that they had to change the name of the operator from convergence to divergence. From a multiplication standpoint, all this works out if you assume the same IJK rules as they did for the dot product. Why did Gibbs and Hamilton do this? Okay, why not just develop something completely new? The answer is that these guys were not trying to develop something new mathematically. They were simply trying to get Maxwell's E and M to be teachable and maybe learnable. Okay, these guys felt that the results that Hamilton, Tate, and Maxwell got were fine. Okay, maybe except for that minus sign and all that weird 4D stuff. But they both wanted these new operations to give the same Maxwellian E and M results, just with fewer headaches. Okay, that's it. What about the new vector product? As we just showed, the vector part of the product of two non-real quaternions is this expression. Okay, what is the analog of this using our new 3D pure real vectors? Okay, if you're following along with the thought process, you might guess that the new vector product, let's call it, the cross product, might be identical to the old vector product, except that, now IJK are all real instead of imaginary. Okay, there's no minus sign to get rid of, so this would leave Maxwell's E and M equations largely unchanged. Okay, say Gibbs and Heavyside, make it so. Well, we run into a problem here. The IJK multiplication rules that we developed for the scalar products don't produce the right answer. What do? I know. Let's make up some new IJK multiplication rules, ones that only apply to the cross product and not the dot product. To indicate this, we'll use the cross X to represent the operation as opposed to the dot that we used before. There, problem solved. And here they are. These are the familiar cross product rules that you have probably been using since high school. Finally, let us consider modifications to the Tate-Maxwell curl operator. Tate defined the curl as the vectorial part of the del operator acting on a quaternion, which is the sum of the three imaginary terms. What is the analog of this for real vectors? Again, driven by the end of getting to the same basic results in Maxwell's E and M, let's not try too hard to rationalize the means we use to get there. Let's just try defining the new curl operator as exactly the same as the old one, except that IJK are now all real, okay? Hey, nothing to it. Okay, now we still have to get those IJK rules to cooperate. Will the ones that we invented for the cross product work for the curl as well? The good news, the answer is affirmative. Okay, this is where I'm going to take a break between parts 1 and 2 of this critical episode. I have just shown you what Gibbs and Heavyside did to quaternions at the fundamental level. And in the next part, I want to show you something about what the implications of these things are, some of what it means. So, get a drink, walk around the room or something, and then get back to work. Okay, see you in a minute, I hope.